Good morning friends. Today we are going to familiar with Johnson counter. It is the shift register counter type. Johnson counter providing feedback from the inverted output of last flip-flop, that is Q bar of the flip-flop output to D input of the first flip-flop. The Q output of each flip-flop is connected to the D input to next flip-flop, but Q bar of last flip-flop is connected to D input of first flip-flop. So it is called also twisted ring counter or Johnson counter. This type of feedback produce a unique sequence of stage that not happen in ring counter. Okay, what is the basic difference between the ring counter and the Johnson counter is the feedback loop. Feedback input from the last flip-flop provided to input of the first flip-flop. In the ring counter, we use the feedback, that is the Q or normal output of the last flip-flop to the input of first flip-flop. But in case of Johnson counter, we used Q bar, that is inverted output of the last flip-flop to use as a feedback to the input of first flip-flop. Due to this, produce a unique sequence of a counter. Okay, next start with example. It is 4-bit Johnson counter. We use the D flip-flop. It is pulling the input as the output. If we feed one input, that output is 1. 0 input as it's pulling output at the output port. The 4-bit stream, it is used flip-flop is n bit. So n is 4. So number of flip-flops are required for the Johnson counter for 4-bit is 4 flip-flops. So we use D flip-flop number 1, 2, 3 and 4. That is, and nominate is D0, D1, D2 and D3. Okay, with the output Q0, that is the normal output, and Q0 bar, that is the inverted output. It is the synchronous type counter, so we used clock at the same time to all the flip-flops. See here, that is the negative triggered is clock pulse to given all the flip-flops at a same time or simultaneous. Okay, this is Q bar of the last flip-flop, that is the inverted output of last flip-flop is feedback from this loop to the input of first flip-flop, that is D0 as the first input of the first flip-flop. Okay, and the output of first flip-flop is connected to input to next flip-flop, that is flip-flop that is D1. And the output of D1, that is Q1 normal output, is connected to input as next flip-flop, that is D2. And the output of D2, that is Q2 is normal output, is connected as an input of D3. And the output of D3, that is Q bar, not Q3. Q3 is normal output, but in this case, that is Johnson counter, we used Q bar, that is the inverted output to feedback to the input of first flip-flop. Okay, this type of feedback produce a unique sequence of states or modes. That how many states are counted by this counter. Johnson counter is counted, the number of states is 2n. N is number of bits. In this example, we used 4-bit. So this counter is used or sequence of state is 2 into 4, that is 8. It means it count from 0 to 7, that is 8 different stages. Let's start. Let's assume all the flip-flops are initially in their states as we take D0 output is 1, D1 is 0, and D2 is 0 and D3 is also 0. It means first flip-flop is set and rest of 3 flip-flops are reset condition. Okay, let's start 1 0 0 0, that is the output of first flip-flop, output of second flip-flop, output of 3 flip-flop and output of 4th flip-flop. Okay, what happened when in the first clock pulse is this we already set the output of like this, set output of all the flip-flops. In the second clock pulse here, in the second clock pulse we get first flip-flop is D0. Okay, it is 1, is D0. Q3 is D0, but Q3 bar is 1. Okay, it is, that is bar, so it is just opposite to this output. It is 0, so Q3 is 1. 1 is feedback by the feedback loop to the input of first flip-flop. So first flip-flop input is in the second clock pulse is 1, and this 1 input is pulling to output, that is Q0. Clear? So it is Q0 is shifted here. Okay, so 1. Second is 1 1 0 0, because this one is also input of D0 and it is shift because it is a shift register, so it shift to next position. So 1 1 0 0. In the third clock pulse it is 0, also it is 1, so it is also shifted to 1 point, that is 1 1 1 and 0. In the fourth it is 1 1 1 and it also 1. In the fifth it is 1, so Q3 is 0, so 0 feedback to input of D0, this means 0 1 1 1. And the next clock pulse, that is a 6th clock pulse, also it is 1, so Q3 bar is 0. 0 is feed to first flip-flop and first flip-flop is to D1. So 0 0 and this is 1 1. Remaining 7th we apply the same process, that is 0 0 0 1, and in the at condition we get 0 0 0 and 1. So after add plus we get its repeat itself like this waveform. Okay, the most important thing of this counter is number of unique states, that is 2n. In case of ring counter, number of states are n instead of 2n. So there each state frequency is equivalent to total frequency ft, that is total frequency divided by n. But in case of Johnson counter or twisted ring counter, the each stage frequency is equal to total frequency, that is ft equal divided by 2n, that is the number of state in the Johnson counter. So it is called divided by 8 circuit. This is 4-bit Johnson counter. 2n, n is 4, so it is 8. So it is called f upon 8, or it is called f divided by 8, that is divided by 8 circuit. Students also learn the advantage of ring counter as well as the Johnson counter. Also application of counter such as frequency measurement, time measurement, electric organs, rhythm generators, atomic clocks, and many more applications from our book. Many more examples are there from the counters chapter. I have shared many more videos for the counter. Basic start for asynchronous counter. There's 2-bit asynchronous counter, 4 up and down, 4-bit asynchronous counter, also for up counter as well as down counter. After that we are familiar with synchronous counter, and synchronous counter is also up counter and as well as down counter, and we selected mode for up and down in a common circuit. And after that we are familiar with very special counters such as shift register counter. They are work as a shift register. Shift register are stored and transfer the data as well as left shift and the right shift, serial or parallel output. In this counter, shift register counter, we have two types, depending on the feedback from output of last flip-flop to input of first flip-flop. So it is count number of state either in sequence or not. In the ring counter, first one is ring counter. The output, that is the normal output of last flip-flop, that is Q, is connected to feedback loop to the first flip-flop. So it is the ring counter. And in the second case, Johnson counter or twisted counter, because it used Q bar, that is inverted output of the last flip-flop, is connected to first flip-flop. So it is called twisted or Johnson counter. Here important is the each state frequency. For the asynchronous counter, synchronous counter, that is the ring counter and the Johnson counter. Asynchronous counter, the each state frequency is equivalent to total frequency is divided by 2 to the power n. N is number of bits. In case of ring counter, we have each state frequency is equivalent to ft, that is total frequency is divided by n. N is number of bits are used in this counter. And finally, the frequency, each state frequency of Johnson counter or twisted counter is equivalent to total frequency ft is divided by 2n, because in Johnson counter we have the states or modes is 2n, n is number of bits. So students, go through many more examples for counters, as well as very important is frequency calculation, each state frequency calculation for asynchronous counter, ring counter and the Johnson counter. These questions is repeat in RTO examination as well as your GATE and other competitive exams. Okay, thank you.